In the preceding video on the normal distribution, I alluded to the fact that the central limit theorem is mind-blowing and really important. So, in this video, we're going to talk a lot about it in order to develop a functional understanding of the central limit theorem. Let's start by sampling some values in code from the normal distribution that we already created. So the normal distribution that we already created, so we've sampled 10,000 values for a normal distribution here, x. And if you want to see what that looks like, so here it is. Here's that distribution x that we plotted out, right? So we created it with the normal method in NumPy. And by default, remember that this will create a standard normal distribution, which has a mean of 0 and a standard deviation of 1, right? So we'll use that vector of values x, and then we can use the NumPy choice method, also from the random module, to select values from our 10,000 values in our distribution here. So let's start off by selecting 10 values. And by setting replace to false, this means that we're sampling without replacement, so we can't sample the same data point from the 10,000 twice. So here's our sample of 10 values from the 10,000. And so with such a small sample, we're not always going to get a mean that's close to 0. So, we know that the true mean is 0, but we're not always going to get a value that's very close to it with a small sample like this. So let's define a function for generating sampling distributions of the mean of a given input distribution. So we're going to take our big distribution x, and then we're going to sample small samples from it, like, with a sample size of 10. And then we'll take the mean of that sample, or all of the samples that we take. If 1,000 times we take 10 samples, then we'll have 1,000 means. And we'll take those 1,000 means and put those means into a distribution. And let's see what that distribution looks like. That's what we're going to do in code here. So we're going to have this sample mean calculator. As inputs, we'll have our input distribution, which is going to be our normal distribution, x. We put in a sample size. So how big is our sample? Let's leave it at 10 for now. So 10 data points, just like this in each sample. And then how many samples will we take? So let's start off with taking 10 samples of size 10. That's what we're going to do here. So this function starts off with an empty list called sample means. And then we iterate over however many samples we're going to have. And in each of those rounds of iteration, we run the code that we ran here, right? So we sample random values from our distribution using this choice method. So this is the distribution that we're sampling from, and for our particular sample size. And again, we are sampling without replacement. After we grab our sample, we append the mean of that sample to our list of sample means. And we do that however many times we set n samples to. And then we return back out of that our list of sample means. So that's our sample mean calculator. Now let's use it. So let's sample from our normal distribution 10 samples. Well, this is the 10 sample argument. 10 samples of size 10. 10 samples of size 10. And we're going to color this distribution green. So here is what that distribution looks like. You can see that it doesn't look particularly normally distributed, but it's not bad. So even with samples of size 10 and only 10 of them, already our sampling distribution which I'm deliberately coloring green because I want our sampling distributions to be a distinct color from the starting distribution. So our starting distribution was blue, and so to distinguish it visually, I'm making the sampling distribution of the means green. So you can see that we tend to have means relatively near zero. They're not hugely off of zero, but they're not always super close to zero. Now, the more samples we take, the more likely that the sampling distribution of the means will be normally distributed. So let's run this same code again, but now instead of taking 10 samples of size 10, we're taking 1,000 samples of size 10. And that's going to be a sufficiently large sample that it's worthwhile turning that kernel density estimate on. So now when we plot it, okay, that's looking pretty darn normally distributed, isn't it? And it's got a mean of 0. So the larger the sample, the tighter the sample means will tend to be around the population mean. So we know that the population mean is 0, and we've already increased the number of samples we're taking. But what if we increase the number of data points in each sample? So let's increase that from 10 to 100 and plot it again. Now I've deliberately fixed the x limit from negative 1.5 to positive 1.5, just as it is here, so that we don't lose the scale of what's happening here. So you can see by increasing the number of samples in each sample before we take the mean of that sample, tightens up our sampling distribution around that value of 0. Our sample means vary less far away from the true mean of 0. And I can make this extremely clear by now increasing each sample size to 1,000, because once I do that, Seaborn struggles with its displot method to draw lines, but it is able to still get that kernel density estimate, and we can see that it's now very, very tight around 0 indeed. So it just gets tighter and tighter and tighter. So the first thing about the central limit theorem is that we get a normal distribution that is centered around the mean of our data points. And the second thing is that as we increase our sample sizes or we increase the number of samples that we take, that distribution will become tighter and tighter and more normally distributed around the true mean. Okay, so it might not blow your mind that the central limit theorem works on normally distributed distribution. So we started with a normal distribution, we're sampling from it, so maybe it's not so surprising that we're getting normal distributions in our sampling distribution. But this holds true with other shapes. I'll show you. So now instead of sampling from a normal distribution, let's sample from a skewed distribution. So we used this RVS method earlier to create a skewed distribution, and let's do it again. And it's actually the same skew as we used before in this notebook, a value of 10 here. And so check this out. So this is clearly a skewed distribution. It's not normally distributed. It has a big skew over out here to the right. Now, let's take some samples. So let's grab 1,000 samples of size 10. So we'll calculate 1,000 means. And check that out. It's normally distributed. So even though the input distribution is highly skewed, our distribution of sample means is normally distributed. And if I increase the sample size, it becomes much tighter around the true mean of our input distribution. So the real mean of this distribution is around here. And by sampling larger samples, so going from samples of 10 to samples of 1,000, just as with the normal distribution, we have a much tighter normal distribution around the mean of the distribution. So I didn't scale things properly here, but you can see the range here. So 0.2 to 1.6 along the x-axis here, whereas now we're just in this tight range from 0.74 to 0.84. So we're centered right around here very tightly. Nice, okay. So maybe you're still not blown away. Because you say, okay, John, well, a skewed distribution, that kind of looks like a normal distribution, a little bit. So I'm not totally impressed yet by the central limit theorem. All right, well, let's try this. Let's now sample from a multimodal distribution. So I'm creating two different normal distributions, each with 5,000 data points in it. One of them is a standard normal distribution with a mean of 0, and the other one, I've set the mean to 4. And then I'm concatenating those two samples together. So here is what that distribution looks like. So it is a multimodal distribution. So a unimodal distribution has just one peak. A multimodal distribution has more than one peak, and specifically this one is a bimodal distribution because it has two peaks. Now let's try sampling from this. So let's use our sample mean calculator to sample 1,000 samples of 1,000 data points each. And nice and normally distributed again, right around the mean of 2 that we would expect when we average our two distributions together. So one of the distributions in here had a mean of 0, and then the other one has a mean of 4. So we'd expect the average of these two distributions to be about 2, and it is. All right. Is your mind blown yet? Hopefully now it is. If not, I've got one more for you. It's sampling from the uniform distribution. So the uniform distribution could not be less normal. It is the most non-normal distribution I could think of. So let's have a look at our uniform distribution from earlier again, right? It's very uniform. It doesn't have any variation. And yet, when we sample 1,000 samples of a size 1,000, we calculate the means of those samples, and we plot them, we get a normal distribution. So hopefully you can see now how powerful the central limit theorem is. It allows us to use Gaussian distributions, to assume Gaussian distributions when we sample data from basically any real-world phenomenon, no matter what the underlying distribution of that phenomenon is. It's a bewildering and highly useful situation. So, as we've seen in this code demo, with large enough sample sizes, we can assume that the sampling distribution of the means will be normally distributed, allowing us to apply statistical and machine learning models that are configured for normally distributed noise, which is often the default assumption, and you can see why now. As an example, the t-test, which we're going to cover later on in these live lessons, allows us to infer whether two samples come from different distributions. Say, an experimental group that receives a drug, a treatment, and a control group that receives a placebo, a sugar pill. So, thanks to the central limit theorem, we can use this test to try to figure out whether the distributions are different, even if we have no idea what the underlying distributions of the populations being tested are, which may be the case more frequently than not. A couple of the notes here is that despite being associated with such a key concept as the central limit theorem, the name normal distribution wasn't originally intended to imply that other distributions are abnormal. It's a historical quirk related to Carl Friedrich Gauss describing orthogonal, so technically we could say normal, equations associated with applied uses of the distribution. So don't think of the normal as like the normal distribution and everything else is abnormal. It's just a semantic quirk. Finally, you may be wondering what the purpose of sampling means is. What's the point of sampling means like this? Well, when we gather data from the real world, we are nearly always sampling a subset of all of the available data produced by a given random process. And once we've collected a sample of data, the aspect of it we're often most interested in, above all else, is its mean. So that's the relevance of sampling means like this and showing the central limit theorem in the way that we've done.